Assalamu alaikum. Welcome to lecture 14 of data mining. So today we will continue and wrap up our discussion on frequent pattern mining. So previously we had discussed some algorithms in frequent pattern mining. We had also discussed some variations and applications of frequent pattern mining. So today we will talk about constraint-based mining. So constraint-based mining actually is a general concept that is applicable to other data mining tasks as well. But of course, we will introduce constraint-based mining in general and then discuss it in bit more detail specifically for the context or for the task of uh, frequent pattern mining. And so that would bring us to the end of chapter 7. 6 and 7 of your textbook, and then we'll start with classification. I will cover the basics of classification and discuss the decision tree algorithm only in this course. And maybe we'll have 2 lectures on classification, and then after that we'll move on to clustering. So we are done with our midterm exam, which was last week. So we are also in the second part of the semester. So you will also be getting your project assignment during this week. So project is also a group activity, a group task that you will have to do as part of this course. And you still have a couple of assignments left. So we have around 14 lectures left as well. So, okay, are there any questions? All right. So let's start talking about constraint-based mining. And so we will start with the basics as well as we'll start with generic, and then we'll move on to its application to item set mining. So I think we talked about interestingness measures first in the introduction part of this course, and we had also discussed interestingness measures as part of item set mining. So just to reiterate a few things, let's say in general, we are talking about descriptive mining. So descriptive mining is typically concerned with finding patterns that are of interest. Okay, from data, of course. So let me define 3 sets. So let's say A, the set of all possible patterns. Okay, so A is a set of all possible patterns from the data. And let's say I is a set of interesting or actionable patterns. Right? So these are the patterns that are really of interest to us, actionable patterns or actionable patterns. And then let's say D is the set of discovered patterns. So these are the patterns that are actually found by the algorithm or found by the data mining process that you're following. Okay? So we have all possible item sets or patterns, and we have the actionable patterns or the interesting patterns, and then we have the discovered patterns. So ideally, so I should be equal to D. So whatever you discover is exactly equal to the set of all interesting patterns. So that would be an ideal scenario. So, so I will probably draw. Just give me a second. Okay, so let's say uh, we talked about the sets AI and D. So if let's say this is a set and both of them are identical, so this is both I as well as D, then of course we are in the best scenario. We have discovered all the interesting patterns. So that's one scenario. So another scenario could be, let's say I is this and D is larger. So this is D and I is inside there. So in this case, we have discovered all the interesting patterns, but we have also found other patterns that are not interesting. So in other words, we are in a way complete because we have found all the interesting patterns, but we are redundant as well. We have found patterns that are not really interesting to us. So we have found lots of patterns. Okay? So that was when you are complete. So in one case, you are exactly the same. You are complete, of course, and you are not redundant. In the second case, you are complete and but you are redundant. And the third case would be, let's say this is I, and you have only found part of it. So this is D here, and this is I here. So only the intersection between D and I is the one that is really interesting. The rest is uh, not interesting. So in this case, you are not even complete now, and of course, you are still redundant. You are finding other patterns that are not really interesting. And of course, if I can draw a whole thing like this, so sorry. So this is a set of all patterns A. So within the possible set of all patterns, we only need I, but our algorithm would find D. And of course, if we are lucky, that D would be equal to I, which would be the best scenario. But in other cases, we would most likely be finding part of I, and we'll be finding some others as well that are not really interesting. Okay? So that is the case in general for all descriptive mining tasks. So in general, basically, I would not be equal to D. So either there will be an intersection, and that intersection may not include the whole of I, and it might include other things from the the set of all patterns A. Okay? So we would like to have algorithm that can give us complete and non-redundant patterns. And of course, and we would like to do this through some processes. So one of the processes that we talked about is interestingness measures, some rules, some constraints. Interestingness measures like support, for example, or confidence, for example. So these were only rules or constraint that we applied on the algorithm so that they were more able to find patterns that were closer to I or included all of I. Okay? So this is the general idea, and we will now generalize this to other types of constraints. Just a second. Okay. So the idea, of course, in data mining is to find all the patterns that are interesting the eye automatically. And this is, of course, practically often not possible. And this is also one of the reasons why our data mining process is interactive and iterative. You have to do it repeatedly. So, to find or to reduce the search space and to find only those patterns that are interesting, we might apply constraints. And constraints can be categorized into various categories. So you can think of constraints as even knowledge type of constraints. So even before you start a data mining task, you decide which task to apply. For example, you have a lots of data set and you have some hypothesis of pieces of knowledge that you like to extract. You will first decide, okay, should I apply a class model as a classification problem, or should I do pattern mining, or should I do clustering, or should I do outlier analysis? So again, right up front, you're doing some type of, you're constraining your process. So that's also a constraint. So it's a knowledge type constraint. Knowledge in the sense that the actual information that you will get out of it, it so that's the constraint. So if you want the pattern to be of in the form of item search, then you'll be doing frequent pattern mining. So data constraints are also constraints, and this is something that we also do almost implicitly without even thinking about it. So whenever we have a data mining problem, we first say, okay, I will apply it on this data set. Maybe you have data set for the past 10 years, but you only apply it for the past 2 years. So again, you're constraining yourself. So again, this is a type of constraint. So this is in general called a data constraint. And of course, you can constrain it not just over time, you can also constrain it in terms of features and types of information that you would like to apply or to do data mining on. So of course, as I said, you can do apply constraints on dimensions, which is also equivalent to features, or also the levels, the granularity of the data. So do you want to do mining on aggregate data for, let's say, stores, or do you want to do mining on aggregate at the level of departments, or do you want to do aggregates at the level of, let's say, cities? So level of is also a data type of constraint. So then we have what is known as rule or pattern constraint. So you can specify your constraint as a rule. Okay, I want uh, patterns that satisfy this given rule. So this is the case that we'll be discussing in more detail shortly. And within this category, we have already looked at some constraints. Like if you talk about the support constraint that we were using in A priori and FP growth, so that's an example of a rule type of constraints. So we are trying to find all patterns that have a support greater than some minimum support. So it's an example of support constraints. So what we are going to do now is to study rule constraints in more general in the context of item set mining and see if we can categorize them in some way, and based on those category, how we can use them in our applications. So instead of having rules that are like that needs to be satisfied, you can also have rules in the forms of templates. Uh, in other words, you are given some part of a rule or some syntax of a rule, and you would like to find all uh, patterns that satisfy that template. So that's called basically template based constraint. So some of the, for example, if you're talking about association rules, so some of those may be instantiated, other might be partially instantiated, and you would like to find all the others that are relevant. So for example, you might specify some conditions like iPad, while other conditions might be open, and you would like to find patterns that satisfy this pattern. So iPad should be there and other conditions would be there, the rest would be open. So if I want to probably give you some example. So for example, maybe I want a rule which is left-hand side could be anything, and right-hand side, it's let's say, uh, you, and let's say this is talking about only buying, or let me say predicate buy, and buy is equal to, let's say, uh, so basically smartwatch, for example. So we would like to know which patterns, which left-hand sides would have a smartwatch on the right-hand side as a item, as a frequent item set. So of course, depending on your other constraint like support and confidence, you might find, let's say on the left-hand side, you might have, let's say, someone who has bought an iPhone. Buy iPhone would basically be someone who buys a watch. Okay, so maybe this one is a strong rule based on your uh, other constraints. But here you are looking for a specific form of the constraint. On the right-hand side, there should be watch. Left-hand side could be anything. So you can specify templates in different ways. So it could be anything. Maybe you say, I want uh, three predicates on left-hand side, and right-hand side could be have just one predicate. So all rules that support the other constraints that also have this pattern would be found. So this is also a type of constraint, of course, in this case, a template constraint. Uh, so of course, since we are talking about predicates, you will probably find rules that have other attribute values as well. So gender is equal to male, for example, and age is equal to, let's say, I don't know, young adult, let's say 20s, and let's say buy is equal to iPhone, and then left right hand side would be, let's say, buy is equal to watch. So this would be an example of a rule that is satisfying this template. Okay. So the summary here is that you can also specify constraints in the form of templates. So templates could be like very simple, like the number of predicates that you want on the left-hand side, the number of predicates on the right-hand side. Templates could also specify some specific things like iPad or iPhone or watch. They could also have other things that you feel are interesting to you and you would like to find rules that contain those specific items or things. So these are called template-based constraints. So now moving back to the more general form of rule constraints. So rule constraints are usually of the form where you have some mathematical way of specifying the constraint. So, and we are already seen some example before. Support of some item set X should be greater than equal to some min sub. Okay? So this is an example of a rule constraint. So you are saying that the item set X should have a support that is greater than some minimum support. Okay? So now we would like to categorize rule constraints based on their, uh, you can say, so let's first categorize them and we will then define their importance. So generally, we have 5 categories of rule constraints. One is anti or anti-monotonic constraint. So then we have monotonic, and then we have what is known as succinct constraint, and the fourth one is what is known as convertible. And finally we have none of the others. Okay? So rule constraints in the context of pattern mining can be divided into these 5 categories. So let's define these constraints and see some examples in each of them. Okay, so let's now first talk about anti-monotone. So the general definition for anti-monotone constraint is, so let's say we talk about a constraint C. C is a constraint, some rule constraint. So C is anti-monotone if uh, if it is violated by a pattern or any pattern X, then it would be violated by all super patterns of X. So these constraints C are called anti-monotone, meaning that if these constraints are violated for any pattern, then we know for sure that they will be violated for all super patterns of that pattern. Okay? So can anyone think of an example? We have already studied one such constraint before. So the support constraint that we talked about earlier, support is greater than equal to, let's say, some value V. This is anti-monotone. Why? Because if the support of a pattern X is less than V, meaning that it occurs less than some fraction V in my transactional database, then any super pattern of X would for sure occur less than V. It will still violate the constraint. ठीक है ना? So let's say you have a pattern, let's say A, B, C. Let's say its support is, let's say, 5%. But my minimum sub is, let's say, 10%. So it means that this support, this item set is not frequent. It violates this constraint. So then, of course, for sure, A, B, C, D would also violate, and A, B, C, F would also violate, and so on. ठीक है ना? So such constraints are called anti-monotone constraint. And of course, support is the most common example for this. So what about some other examples? So let's say count of items in an item set X is less than some value V. So let's say item set X, maybe it's the item that someone purchases at a grocery store. If that count is greater than V, meaning that it violates this constraint, then obviously all super pattern would always violate this constraint, right? So let's say count, let's say, so V, let's say five items. So if an item set already has 5 or more items in it, then obviously super patterns would always have more items in it. So it will always violate this constraint, right? So this is another example of an anti-monotone constraint. So what about, for example, sum of the prices, or it could be any, depending on the problem. Let's say our problem is items set that are sold at a store. So sum of the price of the item sets, if that is less than V, so this is also anti-monotone. Why? Because if you have a basket that contains some items and the sum of the prices of those items is greater than V, meaning that the person has bought, let's say V is, let's say 2000 PKR. Okay? So if someone has bought, let's say 3 items that are greater than 2000 rupees, that means it violates this constraint. Then if he buys any more items, then it will for sure violate this constraint. Okay? So this is another example of a anti-monotone constraint. And of course, there are others as well. There's a example given regarding range of the prices of items within the item set X. Okay? So if the range is let's say greater than V, if it is violated less than V, so this should be the. So this constraint is also anti-monotone. Why? So range, what do you have by range? Let's say you have 3 items that you bought. The cheapest is, let's say 100 rupees, and the maximum is, let's say 5,000 rupees. So range would be 4,900. Okay? The minimum and maximum का जो difference है. Okay? So range is 4,900. If this range is violated for any item set, meaning that if range is greater than the value, then obviously if you add more items in it, you will still have this minimum within it, and you will still violate this constraint. Okay? So this is also a anti-monotone constraint. Okay, so now the question is, we have looked at anti-monotone constraints. So why are these important? So primarily because we can do pattern space pruning. Just like we did pruning for the support constraint in the a priori algorithm, you can do pruning for all of the other anti-monotonic constraint in the a priori algorithm. Okay? So for example, let's say आपने constraint in addition to support, but by the way, multiple supports भी हो सकते हैं. Support should be greater than V. This is one constraint. दूसरी constraint आपकी थी कि let's say sum of the item sets prices is let's say less than V. ठीक है? So now both of these constraints are anti-monotonic, right? So if any pattern at any level of your a priori algorithm violates any of these constraints, obviously its super pattern would also violate. So you don't need to carry that pattern forward, you should prune it. So that's what's meant by pattern space pruning. ठीक है? So let's say, just to give an example, let's say आपके पास A, B, C, let's say इसकी support greater ही थी V से. Let's say minimum support मैंने, let's say इसकी support कर दें 5% है, which is, and min sub आपकी problem की let's say 2% था. So it means the पहली constraint को तो ये violate नहीं कर रहा. But let's say ABC का जो sum है, ABC का, so let's say this is equal to, let's say जो भी है 5000 कर लेते हैं, और आपका जो था वो जो सम की कंस्ट्रेंट की जो कंडीशन थी V की, let's say that was 4000. So it means that it violates this constraint. So obviously you should prune this out because future or higher lengths of this pattern will also violate this constraint. Okay. So this is the main advantage of pattern space, main advantage anti-monotone constraints. They can be used to prune out the patterns in the a priori algorithm. Okay. So now let's look at the other constraints. So we said monotone. So what about monotone, anti-monotone, and now monotone? So monotone, as the name suggests, is opposite. So let's say you have a constraint C. C is monotone if when satisfied by X, then it would be satisfied by all super of X. ठीक है? ठीक है? So anti-monotone was violated, here, satisfied. Satisfied for a given pattern, then super pattern will also be satisfied. So usually these rules are kind of the opposite of the rules that we saw for anti-monotone. So for example, sum of X, let's say price की बात करते हैं, is greater than, let's say, V. So if you have an item set, if you have a basket which has some items, if the sum of the prices of those items is greater than V, meaning that satisfy ho raha hai ye constraint, then obviously if you add more items into the basket, it will always satisfy. Okay? So these are called monotonic constraints. Okay? So what is the advantage for this? Knowing this, so the primary advantage is, so again, in the case of pattern space advantage is no need to check for this constraint once satisfied. ठीक है? ठीक है? So let's say आप a priori algorithm चल रहा है, at any given level, let's say the third level, ABC satisfied the constraint. Then obviously at the higher level, all super patterns of ABC need not be checked because it will always satisfy this constraint. So the advantage here, of course, is reduction in the overhead for checking patterns, whether they satisfy the constraint or not. So we will know for sure that they will satisfy, so we don't need to check. ठीक है? तो of course monotone में और examples भी हैं, count की भी हो सकती, simply reverse the sign and you'll get the it becomes monotonic. So anti-monotonic and monotonic are kind of complementary. But of course, the anti-monotonic constraint yields more advantages because you are able to push this constraint deeper into the algorithm and filter out or prune out patterns that would not be satisfied. So anti-monotonic constraint would produce greater efficiency in the a priori framework. Okay? Of course, monotonic constraint would reduce overhead as well, but the benefit, of course, would be much smaller as compared to for anti-monotonic constraint. Okay? So now let's talk about convertible. So convertible constraints. Any question, by the way? Okay, convertible constraints are originally neither maybe I should discuss yeah, ठीक है, convertible ठीक है. Okay. So neither anti-monotone or monotone in general, but can be made anti-monotone or monotone by a change in ordering of items in item sets. ठीक है? So convertible constraints in general are not monotone or anti-monotone, but they can be made one of those. So the example here, typical example here is the average constraint. Average of, let's say, some item set prices, let's say, is greater than V. V, of course, is a value scalar. Okay? So average of the items in the set X should be greater than V. So let's say मैं 3 items लेता हूँ, 10 है, 15 है, और let's say 20 है. ठीक है, 3 items हैं. इसका एवरेज निकालेंगे तो क्या आएगा? 30 and 45 divided by 3, 15, right? So average 15, ठीक है ना? So if I add a new item, so would the average increase or decrease? Obviously, if you add a new item whose price is less than the largest price in this list, then of course its average will decrease. If it is greater, then it will increase. So if we can control the price of the item that we're adding, then we can make it monotone or anti-monotone. Okay? So let's say typically we do lexicographic ordering A, B, C. Right? A is the first item in item set, B is the second, and C is the third. But let's say so let's say for our example, let's say A की price let's say 15 थी, B की price जो थी वो 10 थी, और C की price let's say थी 20 थी. ठीक है? So now if I order all my item sets according to their prices, now my order would be so B, then A and C. And obviously if I want to grow this pattern, जब इसके बाद कोई भी नया आइटम मैं डालूंगा उसकी प्राइस सी से ज्यादा ही होगी. ठीक है? Because I always write the item sets in ascending order. So C से ज्यादा ही होगी. So if I do that, if I am able to do that, then my average is bound to rise as the pattern grows. ठीक है? It will never decrease, or it will remain the same or increase. ठीक है? So in this case, the rule that I mentioned was average should be greater. Greater, ठीक है ना? So if I do it in ascending order, and if I find that my rule is satisfied, then all future growths of that pattern will always be satisfied because average will always be greater than V. But this is only true when I order the item sets and grow the item sets in ascending order price. Okay?
सर इस एग्जांपल की समझ नहीं आई।
क्या चीज?
सर इस एग्जांपल की समझ नहीं आई।
ये समझ नहीं आई, आपकी बात से क्लियर नहीं हुई।
सर इस एग्जांपल की समझ नहीं आई कन्वर्टेबल की जो आप
ठीक है, ठीक है। सो व्हाट आई एम सेइंग इज कि आपके पास आइटम्स कुछ भी हो सकती हैं। फॉर एग्जांपल मिल्क है, ब्रेड है, ठीक है, एंड लेट्स से यू हैव ए आईपैड, ठीक है ना? सो ऑब्वियसली लेट्स से आपके पास, आपने शुरू में जो आइटम सेट बनाया उसमें सिर्फ मिल्क और ब्रेड है, इसकी एवरेज तो थोड़ी ही है ना, बिकॉज मिल्क एंड ब्रेड आर चीप। बट इसमें लेट्स से आप आईपैड ऐड कर दें, इसकी एवरेज सिग्निफिकेंटली बढ़ जाएगी, राइट? ठीक है ना? सो सिमिलरली लेट्स से इफ यू हैव आईपैड और लेट्स से यू हैव ए कार, इसकी ऑब्वियसली एवरेज ज़्यादा है, अभी तक ज़्यादा है, बट इसमें लेट्स से मैं मिल्क ऐड कर देता हूँ तो एवरेज की सिग्निफिकेंटली ड्रॉप हो जाएगी। ठीक है? इज दिस पॉइंट क्लियर?
यस सर।
ठीक है ना? सो द आइडिया हियर इज दैट वी विल ओनली ग्रो पैटर्न्स इन ए स्पेसिफिक वे ऑफ प्राइस। सो हम कहेंगे कि हमने हमने जो ऑर्डरिंग बना दी, लेट्स से अब मैं उसको ascending order of price में लिख रहा हूँ। A is the cheapest item, B is the next cheapest item, C, D, E, F, G. मतलब G is the most expensive item. So whenever I grow a pattern, let's say मेरे पास एक पैटर्न था A, C था, ठीक है, इसकी एक एवरेज होगी। अब मैं जब इसको ग्रो करूंगा तो ऑब्वियसली आई विल बी एडिंग अनदर आइटम विच इज C के बाद के वाला कोई आइटम ऐड होगा। लेट्स से F ऐड करूंगा मैं, असेंडिंग ऑर्डर में ऐड कर रहा हूँ मैं, तो इसका एवरेज ए सी से हमेशा ज्यादा ही होगा या इक्वल होगा, राइट? बिकॉज एफ इज फॉर श्योर equal or more expensive than C, and of course C is equal or more expensive than A. So if AC की average is greater than V, then ACF की for sure will be greater than V. So this is monotonic. But if we did not have this ordering of items according to its price, then we could not say this was monotone or anti-monotone. So that's the point here. If we had ordered the items in price ascending order, only then can we say a particular, this rule of average is monotone or anti-monotone. So by the way, इस rule को हम उल्टा, इस item sets को उल्टी order कर लें हम, so जो भी हमारे पास item set बनेगा वो पहले वाला बड़ा वाला बनेगा। लेट्स से F है हमारे पास एक सिंगल आइटम सेट, फिर लेट्स से FC है, so FC का average on general would be less than the average of F, and let's say FCA would in general will be less than the average of FC. ठीक है? So in this case now, वो जो हमारी ऊपर constraint, it becomes anti-monotone, because if it violates, meaning that it's less than V, then super patterns or growth of that pattern will also violate. ठीक है? Is this clearer or still some confusion?
सर क्लियर है। मैंने फर्स्ट वाले एग्जाम से एक क्वेश्चन पूछना है। एसी की आपने बात की थी कि जैसे एसी की अगर एवरेज ग्रेटर देन वी है, नहीं एसीएफ की अगर ग्रेटर देन वी है, देन एसी की भी फॉर श्योर ग्रेटर देन वी हो। लेकिन AC तो सुपरसेट नहीं है ACF का।
ACF
हम बेसिकली सेट से सुपरसेट देखते हैं ना, लेकिन ऊपर
जी जी।
वाले केस में हमने
तो लेट्स से
बात की कि
AC
F
जी
ACF की बात की थी ना, कि अगर ACF की एवरेज 20 से ज्यादा है देन
जी
फॉर
जी।
श्योर AC की भी एवरेज 20 से ज्यादा है, क्योंकि
नहीं नहीं,
F
ये नहीं मैं कह रहा।
ये अच्छा
ACF लेट्स से इसकी एवरेज लेट्स से ले लेते हैं, कुछ नंबर ले लेते हैं, लेट्स से इसकी एवरेज 100 है, ठीक है। तो AC की एवरेज if it is in ascending order, let's say, it would be always less than or equal to 100.
ठीक,
So
ओके ओके फिर
assuming
समझ आ गया, ठीक है ठीक है।
so item sets or items are in ascending order of price, ठीक है। So that's what we are saying here. If you always write item sets in some order which is based on the constraint, in this case let's say price, then the average constraint may become monotonic or anti-monotonic. But in general, the average constraint is neither. It will only become one of those if you order the item set in a specific way. And in this case, in a way of ascending or descending price. ठीक है? So इसमें आप अब remember I mentioned the word growth here, right? Because we have to grow the pattern. आपका जो था FP growth algorithm में growth होती थी. So this actually approach or this constraint cannot be easily pushed into the a priori algorithm, cannot work in a priori effectively, but it does work in FP growth. Because FP growth में growth होती है, और growth let's say आपने constraint कर दी according to our criterion of price, then you can apply this constraint to prune out patterns that do not satisfy. बट इन ए प्रायरी में क्या होता है, आप सेट्स बनाते हैं और सेट्स के कैंडिडेट्स बनते हैं, उसका एक स्पेसिफिक तरीका है उन कैंडिडेट से नेक्स्ट कैंडिडेट्स बनते हैं, सो ऑन। उसमें ये कंडीशन सेटिस्फाई होना मुश्किल होती है कि हमेशा ही आप लिख तो सकते हैं एक आइटम सेट को इन प्राइस ऑर्डर, बट जब कैंडिडेट जनरेट कर रहे होते हैं उस वक्त आपके पास कंट्रोल नहीं होता, ठीक है। एंड ऑफन टाइम्स ये जो ऑर्डरिंग है इट विल, okay, if it doesn't contradict your other ordering, then it can work in a priori, but sometimes it will contradict. आपको let's say एक constraint के लिए एक ordering रखनी पड़ रही है, दूसरी constraint के दूसरी ordering रख दी, in any case वो नहीं allowed हो, वो it won't work. एक ही ordering आप रखें, and if for that ordering आपके constraint anti monotonic बन रही है तो a priori में चल जाएगी. And of course it would also work in the FP growth algorithm in this case. So that was convertible. Let's move on to the third or fourth case, which is called succinct. So succinct constraints. So succinct constraints are those constraints that can be satisfied without looking at the data set. So C is succinct. If it can be satisfied without scanning the database. ठीक है? So that's why, of course, succinct का मतलब यही है कि something, I don't know English का लफ्ज़ है, it's so brief or whatever. So it's a constraint that can be satisfied easily. So for example, let's say आपकी constraint है कि एक pattern X or any pattern X should be a subset of some other pattern S. So let's say maybe X is a subset of, let's say, some items. आपने iPad इधर रखा, iPhone रखा, iWatch रखा. So let's say I only want item sets that do have सबसेट कर लें या इन भी कर सकते हैं. दोनों ये जो है ना सबसेट भी और दूसरा जो है एक्स इन. ठीक है. So each item in so I don't know किस तरह mathematically इसको correct कर लें. So each item, if any item in X is in from a set, so let's say V is in, let's say, iPad, iPhone, and let's say iWatch. So this is also succinct. So why is it succinct? So because it's very easy to satisfy this constraint. कोई भी पैटर्न आपके पास आया, आपने सिंपली इस रूल को चेक करना है कि does it contain an item which is iPad or iPhone or iWatch. If it contains any of those items, then it is of course satisfying. So we don't need to actually scan the database, do the counting, and do the other processing that we typically do for the other constraints. So in other words, these constraints can often be checked post hoc, meaning that after you have found all the other constraints, then you can apply and check for these constraints. ठीक है? So for example, कोई भी आपके पास, let's say I found a pattern which is frequent, let's say मैं कहता हूँ iPad, and let's say computer. So let's say this pattern is frequent. So obviously this pattern contains iPad, so this is satisfying. Let's say I have another pattern, computer, printer. Obviously this pattern does not contain any item from the from my desired set of items, iPad, iPhone, or iWatch. So this does not satisfy. So succinct constraint, again, in brief, is any constraint that can be verified or checked without scanning the database. Okay. And then finally, of course, none of the others. So there may be complex constraints that can not fit into the other 4 categories. And of course, there are many such constraints, and you can think of anything else that is sophisticated that would typically fall in this category. Okay. So if we talk about the a priori algorithm, so we are most excited about anti-monotonic constraint because those can be pushed into the algorithm and reduce the complexity of the algorithm. So anti-monotonic constraint can also be pushed in the FP growth algorithm. That's possible also. Convertible algorithms, if they are just one convertible algorithm, then of course it can be pushed into a priori. But if there are multiple convertible algorithms, then a priori cannot do all of them together. Of course, in FP growth algorithm, again, multiple, it won't be handled, but FP growth can handle convertible with other constraints easily. Okay. Because of course, as you know, we do F list there. So, okay, so that's about constraints. And let's see. Any questions? So there are some simple algorithms and examples that are given here. You may look into them. They are pretty easy, of course. I won't go into them. Okay, strongly convertible. If a constraint can be converted either into monotone or anti-monotone, those are called strongly convertible, meaning that they can be converted to both sides. Of course, the example here is average. So average को जब ascending order में करेंगे तो उसकी एक कैटेगरी बनेगी. Items को ascending order में करेंगे तो एक बनेगा, डिसेंडिंग में कर देंगे वो दूसरा बन जाएगा. तो एवरेज इज एन एग्जांपल ऑफ स्ट्रांगली कन्वर्टेबल. So this is the general picture. You can have a bunch of constraints, and the constraints can lie in each of these categories. So they are, of course, convertible constraints. They can be either monotone or anti-monotone. Of course, strongly convertible could be either of those. So ये Venn diagram से यहाँ show किया हुआ इन्होंने. And then, of course, you can have some more examples of constraints that are convertible, and in general, what constraints are succinct and anti-monotone. So you can find them in the slides as well as in the book. Okay. Any questions? All right. So the next topic that we want to start is on classification. And this topic we won't be going to go, we are not going to go in great detail because obviously classification is a big topic that can easily take half of your lecture. But I assume half of your course actually. But I assume classification is covered in fairly fair grade detail in other courses at LUMS, for example, the machine learning courses. So we won't go in detail, too much detail here. I will cover one algorithm, the decision tree algorithm and its variants, some of its modern variants, and which may not be covered as well in machine learning, but it's covered in some other courses. So in any case, they can be overlapped. So I'm going to cover decision tree and some of its variations. Uh, so we'll start with the basic first of all. So of course, classification is a name from machine learning. It's basically supervised machine learning or supervised learning. Supervised learning essentially means that you have data with labels. You train a model. So your knowledge that you get is the model, not a pattern, like in descriptive data mining. So in other words, it's also predictive data mining. So you get a model. So model is the output, not a pattern, like item set is a pattern. Okay? So model is the output. So once you have the model, you can use that model to make predictions. So that's why this is called, of course, predictive data mining. So essentially, what is classification? You can provide definition in multiple ways. I would briefly mention it as a mapping. So classification is a mapping. So you have a mapping function, let's say G, from an input space. I'll mention the space later, to a fixed set of labels. So let's say 1, 2 to capital K. So K in general greater than equal to 2. So these, I've mentioned these labels are 1, 2, 3. You can give them any name. So they are discrete labels. So you can call one, depending on your application, to be, let's say, spam, and 2 could be ham, and so on. And if there are topics, 1 could be science, 2 can be politics, 3 can be sports, 4 can be something else, and so on. Okay? So it's just a label identifying the class. Okay? So so classification is basically learning this mapping function G or model G. What does this model do? It will take your object representation, which is my input space, which could, you can also say your feature space, whatever that is, and it will work on that and give you your output. So if I want to write this again, G, if my input is X, let's say as a vector, let's say I have a representation in terms of vectors. So then of course, X would be from some, let's say m-dimensional real space. So m-dimensional vector represents my object. ठीक है? And then of course, right hand side पे वही होगा 1, 2, k. ठीक है? Of course, input आपका जरूरी नहीं है vector representation में ही हो. It could be in others as well, as long as your computer can process it. It could be a sequence. It could be a sequence from a set of all possible sequences. It could be a graph from a set of all possible graphs. It could be just a single value as well, of course, but that is a very trivial problem. So it could be some space which covers your objects that needs to be classified. ठीक है? Sometimes इसको हम instance space भी कहते हैं from machine learning perspective. Feature space भी कह सकते हैं. Input space यहाँ मैंने लिखा है. You can solve that as well. ठीक है? So, and then of course the output is from a fixed set, 1 to k. If k is equal to 2, we call it binary classification. If k is greater than 2, we say it's multi-class classification. ठीक है? Of course, इसी context में मैं regression भी define कर देता हूँ. Regression. So regression is also supervised learning, similar to that. Supervised learning, it is predictive modeling. It gives you a model, not a pattern as the end result of the data mining task. But the only difference is the mapping function G, of course, your input space, input/instance space, to some real number R, single dimensional real number. Of course, it could be multi-dimensional as well, but most commonly it is the real number. So output is not a label from a fixed set of labels. Now it's a real number. So इसमें of course आपकी example हो सकती है, let's say price prediction हो रही है आपकी, let's say. So output is a number, a value, a price for an item. Input would be an item, output would be price. So for example, price could be price of an item at your store. It could be, for example, the price of a stock, for example, and so on. So output जो आपको आएगी, it's the actual price, a value. So such problems are called regression problems. ठीक है? In both of these cases, you need training data or data for learning. ठीक है? So let me say we have the data. Let's say my input is vectors, which is the most common. X is a vector. I is index of the example or instance in my training data set. And then let's say the output that is also available in the data set is Y. Okay? I. And then of course we have multiple examples. I is equal to 1 to n. Okay? So this is my training data set. So let's say if it is a stock, let's say if it is stock price type of thing, तो आपके पास इस तरह का हो सकता है. PTCL for example एक stock है, उसकी price I don't know what it is, 50 है, let's say. एक और है, let's say net sold for example, उसकी price 55 है. OGDC की price let's say 65 है. तो ये आपके पास data available है. Of course ये मैंने PTCL OGDC लिखा है, तो usually we will be representing these entities with some features. X, not just the name, because name is not very descriptive. So we'll have some features कि उनकी previous history क्या थी price की, last price क्या थी, या उनका last year का profit क्या था, and so on. So we'll have a feature set. And then of course the output is the price. ठीक है? And of course if it is a classification problem, इसी तरह ही let's say कोई topic classification problem है, आपके पास document 1 है, let's say this is sports. So document 2 hai, let's say this is also sports, for example. Document 3 hai, let's say this is politics, and so on. Of course, document 1, document 2, document 3 again needs to be represented with some features. Okay? some x. तो ये ट्रेनिंग डेटा आपके पास होना चाहिए before you can do supervised learning. ठीक है. So now let me just start with decision tree with a few words. We'll do the main discussion of decision tree next time. Tree learning. So decision tree basically is a model. So this is the model that we actually want to learn. Okay? And this is the outcome of our data mining task. Okay? So what exactly is a decision tree? It's of course, it's a specific type of data structure which has nodes, okay, and edges, and usually it is in a hierarchy. Okay? So, and we will discuss this next time in more detail. Nodes generally represent attributes, edges represent their values, and of course, the hierarchy means that we are checking on the values one at a time. So at the start, of course, tree has just one node. It might have multiple edges, and then हर एक edge के बाद फिर node आएगा, then multiple edges. And so internal nodes basically are decision nodes. And then the leaf nodes are the class nodes. So basically, once you reach the leaf, that is the label for your particular data set or example. Okay, so we will see, I think, an example of this next time, and then see how we can learn such a tree. And of course, we will also discuss some more variants of the standard decision tree that are more common nowadays, like the random forest and the boosted decision trees. Okay, so I think I will stop here. Any questions? Any questions? So please continue reading the textbook as well as following up on the lectures as soon as possible. Don't put a big delay between the lectures and the actual reading. I know this is midterm time, maybe you would not be paying too much attention to the lectures, but again, I will recommend you to साथ-साथ आप पढ़ें और देखें, बाद में pile up हो जाएगा, because we will be discussing a number of things the remaining of the semester. So don't leave things behind, follow them up as soon as possible. And also, as I said, आपके अब project भी शुरू होगा, assignments भी हैं, so workload is definitely going to increase. ठीक है? Any question? We will have our next quiz on next Tuesday. ठीक है, इंशाल्लाह. तो ये week भी नहीं था quiz, पिछले week भी नहीं था, तो from Tuesday onward we'll have weekly quizzes again. So 4 हो गए हैं, we'll hopefully have 4 more, and we will drop one.